So we were in the middle of stacks. Two operations you have to remember here are
uh, push and pop, right? So when you push, then so and the open access to this data structure stack is only at one end, which is called the top. So when you push X, it goes to the top, and when you pop, then the top is emptied. The top is removed, and the stack becomes of size one less. Okay, these two things you have to remember, and using that you have to solve in the most elegant way uh, expression evaluation problem. So expression is given in this array, right? So 8 plus 3 star 5 exponentiation 2 minus 9. So this has been inserted inside the stack. The input is this array. So now what we will do is we'll first show the schematics of how stack helps in this. And we have to solve this in very few scans of the array. So yeah, so let us do this in steps. Some ideas were given how to use precedence, but the pseudocode will not be so transparent unless you see this example in the dry run. So let's see. With just one stack. So this will not be the final pseudocode. The final one you have to write at home. I'll just give you first the schematics with one stack and then tell you why you'll need two stacks, or why two stacks will be better. But let's first see with one stack how does the stack model helps in this problem. So I will need some labeling. So this is operator 1, operator 2, operator 3 and operator 4. Right, so you have 4 operators and the remaining things are operands. They are 5, 8, 3, 5, 2, 9. So what do you know about the precedence of the operators? O1 is greater or less or equal to O2. So O1 is less. And what about O2, O3? O3 is also less. And what about O3, O4? Sorry? So what is happening is that if you only focus on the operators, then the precedence may increase or decrease as you move forward in the expression. Right? So here it increases for a while and then it decreases. So the place where you have this local maxima, what do you have to do with that? This is an indication of something. So local maxima at O3 indicates that O3 has to be evaluated immediately. Okay, so which means that 5 raised to 2 has to be calculated immediately. So this is what the main idea is. In fact, this is the only idea. Rest will be implementation. So the idea will be evaluate the operation OI immediately if OI is a local maxima with respect to precedence. Okay, so which means that if you had a situation where O1 was greater than O2, what should you do? Then O1 is a local maxima there because there is no operator before O1. So if O1 is already a local maxima, then you should have evaluated O1 immediately and you should not have waited. But since that is not the case, since O1 is less than O2, so you have to wait. So you postpone the calculation, which means that 8 plus 3 star you have to save it somewhere. This cannot be lost because this will be utilized later. But when you see wedge or this exponentiation, that you can kill right there. Okay, you don't have to postpone that calculation, so you make it 25. So, okay, so how will this work in a stack? Example O3 is a local maxima. So what will happen is if you did this stack pushing incrementally, then you would have pushed 8 and then plus, then 3, then star, and you will reach 5 wedge, and that point you will realize that wedge is going to be a local maxima. So this 5 wedge 2 you will calculate immediately. So this you will calculate and replace this by 25. Is that clear? Yes. Yeah. So this is why this one stack will be will not be very transparent pseudocode. We'll do this again with 2 stacks. We'll keep a stack with operators and we'll keep a stack of operands. But even if you wanted to do this in the pseudocode, it's possible easily because you can go after 2. So then you will see minus. So you have O2, O3, O4, and that will tell you that you are in that O3 is a local maxima. So then you can push these 2, 3 elements from the top, pop these 2, 3 elements, and get to the picture where I have calculated 25. So that is possible. You just have to pop the last 2, 3 numbers or symbols. So when you decide that wedge has to be calculated immediately, then you pop out 2 wedge 5 and push 25. So you are basically popping out, well, let's see minus also. So pop minus 2 wedge 5 and push 25. Okay, this is what you should do. The last 3, 4 symbols you remove, and then do not postpone this 5 wedge 2, 5 exponentiated by 2, and push that value. And now what remains in the array, you can again continue on that path. So that would be 8 plus 3 star 25 and well, so minus 9. So what is happening here? So now this is O1, this is O2, this is O3, and you learn what? Yeah, you learn that now this new O2, so I am changing the labels. Previously we had this. So previously it was like this. Now I am reusing O1, O2, O3 for this new the new stack situation. And now I see that this star is a local maxima. So I should do that calculation immediately, just locally, without involving 8 or 9. Right? So this will then, this whole thing will be replaced by what? 75, just do the multiplication, so you'll get 75 here. 3 times 25. So we have popped, well, 9 was actually not needed anyways. So we have popped minus 25 star 3, and we have pushed the value of O2 operation. O2 operation meaning that the immediate left value and the immediate right value of multiplication. So that's 3 times 25. Okay, next is, so notice how 8 and plus are still waiting, right? They are waiting in the stack. So 8 plus 75 minus 9. What was the whole expression? My whole expression ended at minus 9, okay. Sorry? Well, I am doing it with one stack. So you would have, in the stack you would have pushed minus, or at least you would have observed minus, to decide that O2 is a local maxima. If you don't see minus, then you will then multiply this O2 has to wait, because the next operator could have been anything. Where? In the first, after what? After POP 5. Well, so 5H2 minus. Yeah, 9 is not important, just the operator is important, right? So this was O4, which is how you decided that O3 is a local maxima, and then you can remove this. And push 25, then again after 25 you have to see minus, and so now plus star minus tells you that star is a local maxima. So this suggests that it will be better to use 2 stacks, because you are not looking at the numbers much, you are only looking at the operators. So we'll, on the next slide we'll do it by operand stack and operator stack, but the idea is already here. So now you are at 8 plus 75 minus 9. No, this is these are just 2 or 3 scans. So the array is given in the input. As you are scanning the array from the left, you can keep pushing operators into a stack. And in the stack, and while you are pushing it, you can check whether you have reached a local maxima. So this is just some constant number of scans. It's order n. No, it's not. We are not at the middle. This is a stack, so we are always at the top. No, but that is just, so the 3 or 4 pops are fine. This is order n. No, 9 you don't need to push 9, because this is just, we are only comparing operators. No, stack is the same. There is only one stack. Operations are, the update operations are many, but the data structure is only one. No, not all. We are doing this sequentially. What is happening is in this example is exactly what will happen in the pseudocode step by step. There is no step jumped. Yeah, after O3, whatever is there, we have not even seen it. So O4, O5, On, we have not seen at all. So we are at the beginning. No. How can you cannot scan a stack. No, you have some misunderstanding about stack. Stack, so this orange box is the hard disk, and the red crosses that I am making, only that part is being edited. The hard disk is not being changed. And after the top, the hard disk is empty. So we are only changing these 3 or 4 things at the top, that's all. So this stack could have been very long, so 8, 3, and then there could have been n elements or n by 2 elements, but we are not changing them. They have been just written in the hard disk. They are not being accessed. In fact, they are inaccessible, and definitely they will not be edited. Only the top 2, 3, 4 elements are being edited. No, how can there be n elements? This is the top. At the top you have only one element. The n elements have to sit in the bottom, and the bottom we are not accessing here. So there is some confusion in the semantics here. This is where we are working, and this is the part which is inaccessible. So inaccessible part is what you are saying is n. That we are anyways, won't be able to see that. We can only see the top. So from the top there are only 3, 4 elements that you need to either push or pop and do the decision whether it's a local maxima. Okay, by the way, if when will this inaccessible part be very long? What does it mean about the operators? Yeah, it means that they have continuously been increasing or equal. So that is why it's a long chain, and you were never able to decide what to calculate till there is a fall in the precedence, and then you decide. So that can happen in a general input. Okay, so this example is now ending. We have reached this, there is no other data left. It is just this, and these two operators are kind of equal in precedence. What do you do now? Yeah, so you can now just decide that from the top, I mean again we can only see the top. So from the top we start evaluating. So from the top you can then evaluate this to, maybe I made a mistake in my example. Anyway, so yeah, so just do 75 minus 9. So 66, right? You get here, and then in the end you will get yeah. Are we? I don't know. I just thought they are equal. Yeah, so these things you have to see in your pseudocode. So there are actually many corner cases to be handled. But yeah, here you are at least getting the correct answer. So you can do from the top minus operation, and then you can do the plus operation. So again, there is pop which happens. So 75 minus 9 was removed, or maybe technically I think it should be called plus 75 minus 9. Otherwise the arithmetic changes. If it was minus 75 minus 9, right, then you should have done something else, not got 66. So it's actually plus 75 minus 9. Which we have calculated to 66. Now plus is again the operator to be done on 8 and 66. So this you have to remove and push 74. So that will be the answer. Right, so you have now a stack with a single element, a single integer. So that integer you output as the answer. So this is the rough sketch of the steps in the pseudocode. Yeah. It's a matter of tradition. So if you are just reading this stack, then you have pushed minus and you are checking minus and wedge and star. You are comparing these three to find the local maxima. So there are many invariants here. There are many assumptions which are being let's say followed. So one assumption is that in the stack, even though there may be many elements like n elements, there is no local maxima in it. Okay, because if there was local maxima, then we would have evaluated and removed it, popped out of the stack. So if so, so this is the assumption on the inaccessible part. This is the invariant. So you have to write down those invariants for a correct proof. So there are a number of invariants here. First is that the elements in the base do not have which in particular means that it's a non-decreasing sequence. Because if there was any time if there was a rise and a fall, then you would have a local maxima and you would have done it before. You would have removed it. Right? So this is an invariant, that you have a non-decreasing sequence of precedence, order of precedence. So this is part of the sketch. This follows from the sketch. So that's basically the proof. Else we would have popped it before. As we are incrementally building the stack, we would have popped that out if there was sequence was not non-decreasing of operators. And yeah, that basically is it. So once you observe this and prove this, I think you can see that the pseudocode or this idea will give you the correct answer. But yeah, for a rigorous proof, you have to show that when we push the calculated value, we don't change the value of x. Of the expression. So x was the given expression. So now when you are, for example, in this dry run, when we decided that we'll replace 5 square 5 wedge 2 by 25, at this point you have to show that the expression that you have is exactly equal in value to the input expression. So how do you prove that? Why is that correct? Right, that's also an invariant, that's also a very important, equally important invariant. that whenever you push a value, the original expression value has not changed. Why is that? Yeah, so for this you have to understand how precedence works. What was precedence saying in your expression x? Right. So when you were given this expression x, 8 plus 3 times 5 square minus 9, precedence meant that this middle thing 5 square is equal to 25. Right. So you have to go back and see how precedence dictates the answer of an expression, and the answer is unique. It's not that you will do one precedence rule and your friend will do the same precedence rule and get a different answer. Right? Both of you will get the same answer. So this expression is unique. This has a unique answer, which is said to be unambiguous. So as long as your precedence rule and the expression, as long as it is unambiguous, there is only one answer possible, and show that your stack idea is getting to that unique answer. Right? So that's the final thing you have to prove. So use the unambiguity. Of x. So if x was ambiguous, do you know an example of an ambiguous expression which can have two different answers? Let's see an ambiguous example. So what do you do when you have 5 wedge 2 wedge 3? What is this expression equal to? Sorry? Why can't you first evaluate 2 cube and then 5 raised to 8? Or 5 square, which is 25 raised to cube? Yeah, so there is, so for that, so this, at this stage, this expression y equal to whatever is ambiguous. Right, so then in your rule book you have to add one more rule, which is called left associative. So to make this unambiguous, we say that in addition to precedence there is also associativity rules. So I don't have time to go into all those details, but with only precedence this will not work. So this is ambiguous. As it can be 25 cube or 5 to the 8. Right, so it has two answers. So two friends can get two different answers. So obviously the stack idea or anything will not work because even mathematically this is ambiguous. So to remove that ambiguity, you have to add here left associativity. Which says that when you see such an expression, you should follow the first one and then do the second one. So you have to use, I mean, ideally you should use parenthesis. If you do this in programming, don't rely on this associativity. It can be confusing in the code. Ideally you should just use parenthesis. But mathematically it's correct that the y expression is actually just this. So it is considered 25 cube. And for the, if you meant the other expression, then you should have written what? How do you get 5 to the 8? Then you have to give, then you are forced to put parenthesis like this. Right, and this is not the same as y. So that's why parenthesis is needed, because amongst the two solutions, one follows left associativity rule. And if you meant the second one, then you have to force a parenthesization. Okay, so yeah, that goes inside the proof of your stack implementation for expression evaluation. Any questions? Okay, so to make the code clearer, use two stacks. So one stack will be the, let's call it the n stack. So that's for the operands. So in the operand stacks, you can put the numbers which came. So 8, 3, 5, 2, and 9. And second is the O stack. Of operators. So here you can just keep the operators, which is plus, star, wedge, and minus. Okay, so you can keep them separated, and so when you are pushing in the O stack, plus star and wedge and minus, so you will know that now wedge is a local maxima in the O stack. So that is what has to be calculated first or immediately. So at that point you have to find out what are the inputs of wedge. So you will see by the, I mean in the pseudocode you will have order, so you will now know that the inputs are 2 and 5. So you will calculate 5 wedge 2, pop out 9 to 5 and push what? 5 square, which is 25. And similarly pop out minus and wedge from O stack. So these two stacks will change as described in the previous process. But keeping these two will be a cleaner pseudocode which you should write. So write this pseudocode. So that is one, that's a simpler assignment. This will not be very difficult. It's already described. So write this pseudocode using n stack, O stack, give an expression in an array. Now modify that pseudocode to handle parentheses. Okay, so how do you handle parentheses? So this, and so basically just brackets. How do you handle these? Correct. Yeah, exactly. So again, this is one of the precedence rules that when you see parentheses, the parenthesized part holds the highest importance. So when you see an open parentheses, then you think of that as the base of the stack. So this means an artificial base of the stack. Base, so it's an artificial base. You consider this as your current base of the stack because everything above it has to be calculated first, no matter what, and removed from the stack, answer put, and only then you are allowed to see anything at the actual base of the stack, right? So this makes open parentheses means that you have basically started from the base of the stack, and then maybe another open parenthesis comes, so then the base shifts there, artificial base shifts there, and so this may happen obviously unbounded many times, depends on the input. But at some point there will be a closed parenthesis if you wait very long. And the closed parenthesis then means that you should close the calculation till the current artificial base. Right? So that part has to be done. So this is again kind of stack inside a stack. Right? So it's not very difficult to implement, but still first time you have to do it. So change the pseudocode for this. So this means that the substack value has to be calculated. Okay, so when you see closed, then you have to calculate from artificial base to this point that value. So the fragment of the pseudocode will still be what you have written before. The fundamental pseudocode is not changing, but it's just that now there are more layers. You need one or two more variables to keep track of these things. So that will handle parentheses also. So I think, yeah, that should be enough for you, enough hint for you. Any questions at this point? So this will take few hours to finish, so this is why I'm not doing it here. You do it at home. One important thing about stack is, so this is very important for operating systems because do you know how your recursive C code is implemented by the OS? Yeah, so when you write a recursive C code, this is a challenge, you are giving a challenge to the OS because you are not telling it, giving it the explicit loop or the for loop, the iteration, but you are actually leaving it to the OS to implement it, the loop for you. So the way OS implements recursion is through stack. So the operating system creates its own stack, and when you make a recursive call, and the recursive call, first call makes a second call makes a third call, so those are being pushed in a stack. Okay, so there is a stack of the OS in which the first call values are pushed, then the second call values are pushed, third call values are pushed, and when they are popped, they are being evaluated at the base case of your recursion. Okay, so stack is a very important data structure or idea which allows you to just simply do a recursion without thinking how it is done. It's a shortcut for you. Your recursive C code. So your recursive C code is a stack. So the operating system is basically pushing your call 1 data value here, and then call 2 on top, call 3 on top of that, and so on. And the last call is where the recursion reaches the base case. So that is where the answer is known. So once that answer is known, let's say call 3 answer is known, this the OS will use to answer call 2, which it will use to answer call 1. Okay, so stack is a perfect data structure. It is made in heaven for recursive programming. Okay, if this was not there, then implementation of OS will be very slow. Okay, so if no questions, then I'll throw the next data structure at you. So this behavior of stack is also called especially in OS circles, it is called LIFO. What is LIFO? So LIFO is last in first out, which is at whatever comes last at the top, which pushed last. When you pop, you will see it first, right? A more natural strategy would be FIFO, right? First in, first out. So that is called queue. So a more fair way, at least for human beings, is FIFO, right? If you go to an office, then if you are first there, then you want first out. You don't want LIFO. You don't want to be put in a stack. If you are put in a stack, then revolutions happen. So to stop that, we have a data structure which is called queue. So queue has, so now necessarily you will need both the ends. So there is a, now we'll call it front, which we were calling in the stack top. So there will be a front and there will be a rear of the data structure. So this is the front at A1. So when you want to access something from the queue, then the first thing you will see is A1. Okay, so I put outside arrow, and when you insert something in the queue, then what you will see is this part at AN, so that's the rear. So for this we have to first see what is the mathematical modeling, what is allowed and what is not available. So amongst query operations, the only thing that is available is looking at the front. Okay, so you have the usual thing is empty code, is empty function, which checks whether the queue is empty or not, and more interesting is the front function, which tells you you have to return the value of A1. Okay, so there is no function for rear, so you cannot see what is stored there. So when you access, you will only access, I mean the only function implemented is front. Update operation is the usual one, which is create empty queue. Okay, this is the initialization step, and more interesting is enqueue, X in queue. So what this does is inserts X at the rear. Okay, so enqueue is the insertion analog here. So when you want to insert X, then it will be inserted at the rear part. So you will have a AN plus 1. The queue grows by one, size 1. And the deletion analog here is DQ. So what dq will do? So what have you learned till now about q? So when you delete, then only thing you have access to is the front. That's so you will get that value and it will be deleted. So delete and return the front. So let's say you do nqx in the q. So this is the front, this notation we can use for rear. So what will this give you? Like the stack, this parenthesis I use for the front or top, and the brace I use for the rear of the q. So when you nqx, it becomes what? Sorry? Yeah, so an comma x, you get that. So that is now an plus 1. Is that clear? And when you dq from here, then you will get what? Then a1 is gone, so you will get a1, and the side effect on the q is this, you get a2. Is that clear? So just to be sure, this notation is here you have the front and this is the rear. So it's not that rear is like stack, it is completely inaccessible. So both the ends are accessible, but only 50%. They are accessible to one operation each. So front is accessible to dq or what was that? Front. Those functions, and rear is accessible only to nq. Is this clear? So that is q, the data structure q. So just to check whether you were sleeping. So what is the complexity of accessing AI? O of what? It's I, right? Because A1 is at the front. So if you want to access AI, then the only way is that you have to keep dequeuing, then you will reach after I steps. So okay, so now, so that's once the mathematical model is clear, the next question is how do you implement this? I guess you can implement it using array or pointers. Many ways are there. So let's start with array because there will be an interesting fact there. Okay, so yeah, I won't be able to give the details here, but in an array, what you have to do is the obvious thing, which is array is growing only in one direction. So this is your 0th element, first element, second element, dot dot. Last one is, let's say, n minus 1th element, and you want to implement a queue here. So you need the two tracking variables, front and rear, right? So you should have those things stored separately. So say this is the front and somewhere here is the rear. So you will need the array pointer and you will need the indices, these variables front and rear which track the indices, and then you can, your Q is in this part of the array, sub array, and you can implement all the operations easily. Okay, but there will be one problem in this which we'll solve next time. Okay, thanks.